Our next speaker today is Max Henkart, who's going to be presenting a topic very near and dear to my heart, which is 12 plus image quality attributes that impact computer vision. So Max is an optical engineer who believes that optics matter as much as computer vision algorithms. He has a degree in optical engineering from the University of Rochester, and then went on to be an optical engineer and sales manager at Sonex, where he was responsible for the development of 25 lenses and camera modules. After that, he got an MBA at Carnegie Mellon, and then founded Commonlands, setting it up to help people from different domains navigate through optical and imaging hardware. And he's developed some free online camera calculators that are available at his website, and works helping companies navigate through the imaging hardware world. Thank you. Over to you, Max.
Great. Thank you, John. Hi, everybody. As John mentioned, my name is Max Henkart. I'm an optical engineer, and today I wanted to share one of my interests and passions, which is the intersection of camera hardware, firmware, and computer vision. So this talk is really intended to help provide a framework for computer vision engineers to talk succinctly with their hardware teams, and if you're on the hardware side, also to demonstrate why your hard efforts in image quality tuning and image quality hardware really matters to the end application for your company. So with that, we'll quickly go through additional motivation for why image quality matters to computer vision, then introduce two major categories of image quality, subjective and objective, followed by going through 12 to 14 image quality attributes that can actually impact your computer vision, and I suggest taking into consideration when designing a new camera system. So, embedded vision systems really take a lot of different domain experts to have high accuracy, from optical and mechanical engineers to electrical and firmware engineers and image quality teams. This is the output from those teams is the input to many computer vision, to embedded vision systems. So I just wanted to get a show of hands. Who here is a computer vision engineer? Okay, and who's from the hardware world? Okay, great. So we have a good overlap. So when designing a camera system, it's important to take into consideration the illumination and scene characteristics, the lens design and alignment with the sensor characteristics and image capture process, along with your PCB characteristics and layout, and your ISP tuning. We'll go through a bunch of these in a second. So from the computer vision world, there's something called the one pixel attack. Who has heard of the one pixel attack? Okay. So for those of you who are not familiar with this, the one pixel attack is where researchers changed the level of a single pixel in a classification neural network. And it turned the output of the classification network from a ship to a car, a horse to a frog, a deer to an airplane, just with a single pixel intensity change. It's not very much of a leap to think that something similar like this could occur in the real world. And I'll quote directly from a research paper by Pezzamente, who does agricultural robotics in Pittsburgh. Nonetheless, we show some examples of situations where nearly imperceptible image modifications can result in dramatic perception changes. Even in applications without malicious people trying to trick your system, the natural world may be adversarial enough. So through this talk, I'll extend this to say the natural world, your camera hardware and image processing pipeline may be adversarial enough to your computer vision. So before we get into the specific metrics, I wanted to introduce two main categories of image quality: objective and subjective. Objective image quality is independent of human visual system preference. It's usually measured with image quality test charts in a laboratory setting for repeatability and high performance measurements. When you hear the words, oh, the signal to noise is 70 dB, the resolution or ESFR is 20% at 100 line pairs per millimeter, or the color accuracy is 2. These are objective image quality statements. Subjective image quality is something that is more familiar to most people, because if you have a photo sharing app like Instagram and you look at a photo, you might say, oh, I really like that image. You might not be able to characterize exactly why you like that image, but if it's a bad image, you'll say, oh, that's too grainy, that's too blurry, or it's not colorful enough. These are subjective statements relating to image quality. But subjective image quality does not mean it's not measurable. Subjective image quality is measurable, and the team at Eastman Kodak in the 20th century spent decades coming up with statistical methods to measure subjective image quality, and they arrived at, you can plot what people's preferences are based upon the saturation of an image, and they come up with this term, just noticeable differences. So objective and subjective were introduced and defined by those teams in the 20th century. But does that translate into the world of embedded vision systems? Maybe, maybe not. I don't think that computer vision is subjective by any means. So, well, I mean, it can be, but that's a longer conversation. So in place of objective image quality, today I'll be referring to it as engineering-based, which provides actionable feedback to hardware engineers and image quality engineers so that they can refine their systems iteratively throughout the development process using test charts and objective standards. Whereas on the computational side, the inputs are once again related to human visual cognition and structural fidelity and color, but it also includes content-aware image processing, which is common in digital imaging pipelines. You can't measure content-based image quality very easily because it changes in the real world. So we're going to look at engineering and computational-based image quality metrics for a number of different items. We'll go quickly through exposure, dynamic range, noise, color, shading, resolution, distortion, texture blur, stray light, fringing, blemishes, and dead pixels. Because we're in an auditorium with a projector, sometimes it's difficult to see these image quality artifacts. So if you scan the QR code, it will actually take you to a link on a website where you can zoom into the images. The QR code will be on every slide, so if you forget now, it's okay. So let's start with exposure and define what it is. Exposure is basically a DC offset in the brightness of an image. In this center image, you see a well-exposed image in the top. On the bottom left, you see an underexposed image. It's difficult even for the human viewer to read the license plate. In an overexposed image, it's hard to see the streetlights or the tree behind the car. Exposure can be measured using white, gray, and black patches, and it impacts computer vision even if you augment your data set, as shown in this paper, which you can also open on the website. The network resilience for exposure bias for MobileNet and ResNet in this implementation drops significantly in overexposed images for both networks that are trained with a range of exposure values and without. This just goes to show when you're going through your camera development process to take into mind how your system is performing auto exposure and gain compensation. Closely related to exposure is motion blur. When you are in low light conditions, sometimes you want to increase your exposure length. This can result in motion blur when an object or the camera is moving too fast relative to the exposure length. If you have your cell phone out and you're at night taking an image of yourself, it can be very difficult, and you'll see the streaks and blurs across the object that you're taking an image of. In this case, you can see the butterfly is clear in the top left, and the hidden layers are activated. The activations in the hidden layers are fairly precise. When you introduce motion blur into the system, those become more imprecise. And there are two different types of motion blur. There's angular, so if the camera is shifting, and there's also length for the motion blur. Both can degrade the accuracy of CNNs, and this is a VGG network. Oh, that's the wrong direction. So exposure is a DC offset in brightness. It is not the range from the brightest to the darkest part of the image. That's dynamic range. Dynamic range is the brightest bright to the darkest dark in an image. The real world has dynamic range of over 200 dB, and most modern cameras can be anywhere in the 100 to 200 dB range, depending on how you want to get into the technicalities. Dynamic range is prevalent even in the human eye. If you're in a tunnel and looking out at the end and it's a bright sunny day, you might not be able to resolve the car at the end of the tunnel just because your eye isn't exposed properly and the dynamic range isn't large enough. In this case, within a cathedral, looking through the stained glass, there's a low dynamic range image on the left, and then a high dynamic range. There's two different versions of the same high dynamic range image on the center and the right. With dynamic range that does not match the scene, you can lose feature details in the areas that appear to be overexposed and underexposed. But that can be a little bit confusing when you say the word over and underexposed, because the scene is not, you have to look at the scene average when talking about if it's properly exposed. So a lot of the innovation in camera hardware in the recent years has been to extend the dynamic range of the camera system. This can be performed in multiple ways, from temporal multiplexing, from changing the gain and exposure length based upon frame. It can also be performed spatially using alternate row, so different gains and exposures per row. And it can also be performed using split pixel architectures with different sensitivities per pixel. Even these modern HDR multiplexing techniques can introduce other artifacts into your system. So here are a couple of examples. The left is cropping, where you can see the color differences laterally within the image. The center is ghosting, where an object which is not even present in the scene shows up. But more commonly, you see a signal-to-noise discontinuity. So when you're looking at an object that has the uniform color or exposure across the entire region, due to localized denoising algorithms, sometimes you can see a different amount of noise, and the denoising affects this differently. And we'll get into why that matters once we get to texture blur, but this is related to texture blur. So moving from high dynamic range, and we just touched on noise, so it's a good time to introduce noise. So noise is the variation from the norm of a pixel intensity. Take these sailboat images. The one on the left, it has a little bit of noise, a little bit of too much grain for the human viewer. But if you look at the rightmost sailboat, you definitely will say there is a lot of graininess to this image. While the human perception system can still determine, well, that's definitely a sailboat, computer vision networks, not necessarily so. In this case, you can see that the VGG network has substantially lower confidence that this is a sailboat in the rightmost image versus the leftmost image. Noise can occur in both temporal and spatial domains. So temporal, you can think of a single pixel changing in value from frame to frame. And spatial or fixed pattern is what you see here on the screen. Noise can be measured with signal-to-noise ratios and noise power spectrum in the lab for the engineering-based feedback. So moving from noise, let's quickly touch on color. Color and white balance go hand in hand. You may be able to train your network or use a reference network that has a set white balance or color. And if you don't train on what you actually expect in the field, sometimes the class and the computer vision accuracy can go down substantially. So here's an example of a cat with the objectively correct white balance. It might not be the subjectively best or computationally best white balance, but the computer vision ResNet is able to detect it correctly. Whereas if you shift up the temperature to be too hot, so there's a couple of ways to describe that, but a red shift in the image in white balance is typically too hot. The cat is now identified as a carton. Similarly, if you cold shift the white balance, this dog turns into a snorkel. That can't be correct. Outside of classification, you can also see the impact of color constancy and the correct color on segmentation. So with this vehicle, you see in the background specifically, a grass wall, which is identified correctly as a plant/grass with the correct white balance. But when the image is shifted to the cold side, part of the plant turns into a rock and part of the road turns into the floor. This is problematic if you're trying to perform safety critical applications and you identify the road as a different object. And color can be characterized with color accuracy and in terms of temperature offset. Closely related to color and dynamic range is tone mapping. So this is when your camera hardware does not match the media which you're displaying the images on, and it's required to map from either one bit rate to another or from one color space to another. Here's an example of two different, so it's the same image, they're just tone mapped differently. You can see the structural fidelity in the roof of the cathedral is quite clear in the top, but in the bottom it isn't, and that's just due to tone mapping. It's just something to be aware of. There's no right or wrong. You just have to tweak this in the camera development process, and it does impact computer vision at every scale. So that brings us to shading. We've already talked about noise. And so from noise, we can go into shading, which is commonly referred to as vignetting from a lens. But shading can also be due to uneven illumination in the scene. And so either due to vignetting or inconsistent illumination in the scene, you have reduced signal in the corners relative to the center. Even the human observer in this image, you can easily read the letters Pacific Internet. But when you look into the corners, it's hard to tell whether there is text or what even those objects are. Even if you apply lens shading correction to bring up the signal on the outer parts of the region or of the image, that can also increase your noise. So your dynamic range in the corner is going to be slightly different than the center. And going back to our dynamic range point earlier, that can impact your computer vision performance in the center relative to the corners of the image. And here are, in the frequency domain, you can see the features in the computer vision. And if you ingest these into your network, you'll see it's quite well-defined in the center, but towards the edges, the signal is very noisy. It can be characterized using a flat field target, and when you're talking to hardware engineers, luminance non-uniformity or lightness non-uniformity. But shading is not always just due to vignetting. It can also occur in the color domain. So there can be color shading artifacts. Here's an example with Mario and Luigi. The center golf ball is slightly green tinted. On this display, it might be difficult to see, but is green shifted relative to the leftmost golf ball, which is red shifted. This has a similar impact as luminance shading, but it's in different color channels. So this is a result of optical artifacts such as CRA mismatch, so chief ray angle mismatch, or IR filter walk-off. And ideally, this doesn't get to the computer vision network, but if you see this when you're developing a camera, you just have to go through some additional calibration steps and potentially change your hardware. So we've gone through a few of the major parts of image quality: exposure, dynamic range, noise, and color. The fifth large topic is resolution. Everybody has a cell phone. Sometimes you'll hear cell phone manufacturers saying, oh, we released a 64 megapixel camera, or we released a 108 megapixel camera, or if you have an iPhone, you still have 12 megapixels, which is great for reasons we'll get into. That is one type of resolution. That is the pixel count resolution, so it's the number of receptors on the sensor. Resolution comes in many flavors. There's optical resolution, which is the MTF of your lens and cover glass and the sensor. There's system resolution, which is SFR and includes image processing. And the other major type is angular resolution. Angular resolution, you can think of as magnification or zoom. So your 1x camera versus your 2x camera has different angular resolution. Combined angular resolution and system resolution can define the sharpness of an edge in your image. The total pixel count resolution is also important because it can indicate, not always, there's additional functionality on board your camera, such as high dynamic range, split pixel, or other advanced functions. So we'll quickly go through SFR and angular resolution. But they're all important to computer vision. And here's an example from a surveillance system that is performing pose estimation. You can see the pedestrians in the upper left part of the image. There's two issues with their location in this image. One, they're fairly far away, so the angular resolution is low. And two, the SFR, especially across the person on the right, his arm, you can see that there's some SFR, some blurriness, I should say. And so in these two pose estimations, you can see that the arm and the facing direction is different than what the human observer would estimate. And this can be problematic, especially if you're trying to do threat detection. So are they going to pull out a weapon, or do some inverse reinforcement learning to figure out where they're going, or analytics on what people are looking at in the scene. So I'll group lens MTF and system resolution into one category, which is SFR, because lens MTF is one input into system resolution. This is, the layman's term is it's blurry, which is an oversimplification for people in the image quality world, but let's leave it at that for now. Let's look at the bicyclist in the center. You have a sharp image and a blurry image. The human visual system can tell that it's still a biker in the blurry image, and you can also identify the facial expression and the direction that the biker is looking. In computer vision, there's also similar issues with accuracy. In the sharp image, it clearly differentiates between the biker and the bike, whereas in the blurry image, it thinks the biker is the bike. On the engineering side of SFR, there are numerous ways to perform this measurement with edge SFR, slant edge targets with sinusoidal Siemens star charts and MTF benches for the lens. And it's worth noting that a lot of these engineering-based metrics are not necessarily the same in the field because of localized sharpening that is performed by many image processing pipelines. SFR is also closely related to JPEG compression artifacts. In this example, the image pairs on the left and the center, so the flowers in the city, are, to the human, visually identical. If you zoom in on the website, you'll see the difference map for the JPEG compression artifacts. And on the right, you see dissimilar objects with very different shapes. For this CNN, without any pre-processing or geometric computer vision prior, the difference between the visually identical images with JPEG compression is the same as these entirely different images. So it's just worth noting that if you have to compress your image, be aware of the JPEG compression artifacts that may be introduced. There are more than 10 of those, and it requires an entire talk by itself. But you can see aliasing and ringing and blocking based upon the JPEG compression quality. That brings us to the second major type of resolution, angular resolution or magnification. This, for computer vision engineers, is the scale of an object in the image. Here's an example of pedestrian height. This is an outdated paper from over 10 years ago, but many of the concepts still apply in terms of the accuracy of feature extraction. So angular resolution determines how many pixels were across the pedestrian, his arm. And it is the number of pixels per unit distance in the object or pixels per degree. In the defense world, they like to call it instantaneous field of view or IFOV. And usually more pixels are better, but that's the takeaway from this. But angular resolution is not always constant across the field of view. Angular resolution can change as a function of field, and that's primarily due to distortion. So distortion is the change in angular resolution or magnification across the field of view. Why does distortion matter to computer vision? Well, if you train a network on a reference data set that is undistorted and expect to run that real time on a distorted image, you can quickly lose performance. So it's always best to train on the camera system that you're going to be deploying in the field. You can see the impact on activations in these hidden layers. So this is from the same paper as before. Additionally, it can impact the aspect ratio or the perspective distortion of an object. So in the bottom right, you'll see two golf balls. Golf balls are supposed to be circular, but in this case, they're not. They're actually, the one on the left has a negative F theta distortion profile where it's squeezed, and then the rectilinear, which is actually completely undistorted, you'll see that the golf ball is almost twice as wide as it is tall. So distortion can be characterized by a percent relative to a reference projection. It can also impact easier tasks such as OCR or license plate recognition. In this case, even the human viewer, it's challenging to tell in the left image if it's a W or a V in the license plate. But on the right, with increased angular resolution, it's a little bit more apparent that the letter is a W. So angular resolution impacts geometric and neural network-based computer vision. In line segment detection, distortion is particularly problematic, especially if you don't have the ability to rectify the image prior to identifying the lines. So in high frame rate applications, you might not be able to do the rectification. And in this example, I would look at the bottom row of images. On the right is ground truth, so an annotator drew the lines, and with these 4 networks for line detection, you can see a lot of inaccuracies with the line estimation, and you may need additional line segments to increase the accuracy. So let's move on to the final note about resolution, which is something called texture SFR. This is closely related to noise, and most digital imaging pipelines perform local denoising, and denoising in image sensors is essentially a high-frequency filter, and it can remove a lot of texture from an object. In this case, we have a brick wall building with a lot of detail. The gradient map performed by an edge detector is on the top right, and that information is present. So even if that is too much information for your system, you can easily remove that amount of texture to yield the bottom image, which is the image with texture loss. It's the same image of the building. So let's move on to a few other image quality artifacts. These are not the pillars of image quality, but are also worth taking into consideration when building an embedded vision system. The first is stray light. Stray light can be caused by any optical surface in front of the image sensor. So whether that's your windshield or a lens element or sensor cover glass, this can introduce stray light. Stray light can be veiling glare. It can be flare, which is a streak. If you put a fingerprint on your mobile phone camera, that's flare. The other type is ghosting, which is, you can think of Hollywood when they have that artistic lens. They call it lens flare, but that's ghosting. Stray light reduces the contrast of the image. In this case, even the human viewer is unable to easily detect the vehicle that is behind this dusty windshield. And on the right, it is very evident that there's a vehicle there. So another optical artifact is fringing, the first of which is chromatic aberration, lateral chromatic aberration for the hardware and optics people in the room. This can result in an offset of the color channels around high contrast edges. So it can look like a purple fringe around a high contrast edge. It can also be slightly blue on the inside. There are ways to compensate for chromatic aberration, or lateral chromatic aberration, not longitudinal, in software, but it can introduce other artifacts. In this case, there's a halo, a white halo around the high contrast edge as a result of removing lateral chromatic aberration. The other type of artifact that is commonly mistaken as chromatic aberration, only chromatic aberration, is purple fringing. So purple fringing is related to chromatic aberration, but it's also related to sensor blooming, where some pixels will be oversaturated, and the signal will, so the photons will leak into the nearby pixels. And it's also dependent upon the IR cutoff filter of the camera. So that takes us to the last 2 topics that I'll cover today. The first is image blemishes. Here's an example of a very extreme case of image blemishes. Usually image blemishes are quite small, and they are pinpricks of lower intensity due to dust on the image sensor, but image blemishes can also occur due to dust or moisture in or on the lens. Blemishes usually can be overcome if you're using a detection method, because you'll still have some features that can be extracted from the partially occluded object, but in some cases it will be a method that fully occludes an object, and your computer vision could run into issues Segmentation is much more sensitive to blemishes. In this case, both the human visual system and the segmentation is quite uncertain whether there's a road or a tree where this raindrop is located in the image. If you're interested in blemishes, definitely check out this work. They're doing a lot of GAN-based fill-in and hallucinating regions of the image that allow automotive safety critical systems to estimate what's in the scene. And so that brings us back to the beginning, which is dead pixels. So dead pixels and defective pixels are the real-world corollary to the single pixel attack, which changed a horse into a frog. Dead pixels are typically solved for in the manufacturing process and or calibrated at end of line. But you can also see defective pixels or variance in pixel sensitivity, which is more prevalent. If, for whatever reason, you do get a dead pixel in your embedded vision system, you may see this in the real world. So I hope by running through these 12 different artifacts, we've been able to discuss and show how your embedded vision system, even though there aren't malicious people trying to trick the system by putting stickers in the field of view, the natural world, your camera hardware, and your image processing pipeline, it might be adversarial enough. So today, this talk was mainly just to give you a brief introduction into each one of these image quality metrics. Each one of these is a 2 to 4 hour workshop at the Electronic Imaging Conference in January. So if you want to actually learn in depth all of the engineering topics that go into each image quality metric, I would highly recommend attending that conference. The IEEE P2020 Automotive Image Quality Working Group is working on and releasing a paper that is directly related to image quality for computer vision. Additionally, there is a talk later today down on the exhibition floor by Algolux. They have more of a prescriptive solution to image quality. And feel free to reach out to me directly if you have any questions or thoughts about the various image quality metrics covered. All of these images are shown on the website. You can reach at commonlands.com/summit2020. And I will upload a transcript so that you can share it with your colleagues. Expect that by end of week. Thank you, and I'll turn it back to John to open up questions.
Thank you, Max, for Thank you, Max, for a very illuminating talk. A round of applause for Max, please. And we will be taking questions if you can make your way to the microphone. While you're doing that, I have one to ask. How important is it to consider part-to-part variations, particularly in optics and image sensors?
So part-to-part variation, there are, depending upon the volumes that you're making, part-to-part can impact SFR or sharpness in the image. So getting back to the edge slant and lens MTF. So if you need consistently sharp images from unit to unit for your computer vision to work accurate every time, it is really important to dial in the ESFR and lens MTF. And images can also be blurrier and are usually blurrier around the corners due to the lens MTF degradation or lens alignment. The other thing with part-to-part alignment is color calibration. Sometimes it is really important to do unit-to-unit color calibration because of the IR cutoff filter will actually have a wavelength shift from unit to unit. So you can see a change in saturation or color balance from camera to camera, and that can impact your computer vision if you haven't trained on real-world systems from a large number of units.
Thank you. Let's have the first question, please.
Thank you very much for the very informative presentation. And while I'm digesting everything, I just wanted to understand I took away from your presentation that the image quality really matters on the performance of the computer vision, and I think one of the reasons is because there is a difference between the training data set and the actual input images, and also on the other hand, I also think that the definition of good quality input image is somehow different from for human eyes and the computer vision. So which do you think matters more? And this question, I think, implies what kind of the approaches we should take to mitigate this gap if we should prepare more variety of image training data set, including every possible parameter, image quality parameter space, or to control the camera precisely to result in the specific certain image quality. So do you have it?
Yeah, so this gets to the standard tension between computer vision engineering teams and hardware engineering teams, where the answer is, I'm a computer vision engineer, make the camera and the image perfect. And the answer is that's not always possible. On the other side, from a hardware engineering standpoint, the answer is, okay, well, can you just make a better model or train on more data? And it does help, but as shown in the exposure slide, for example, even if you train on more data and more real-world use cases, it doesn't necessarily completely mitigate the issues that arise by varying image quality. So it really takes a team effort on both the hardware, the firmware, and the software side to get good accuracy in the computer vision.
So technically speaking, so both works to achieve higher.
The answer is yes, and 80% of the effort is required to get the last 10%. So it really comes down to what is good enough. And that's where I always recommend stepping back and taking a subjective user feedback survey, because even as a computer vision engineer, you might subjectively say this image is great, but your computer vision model might perform a little bit differently. And so that can also introduce some bias. But yeah, there's always incremental improvement that can be had on image quality and on the computer vision side. So it really takes continuous improvement through manufacturing and development of the algorithms.
Yeah, thank you very much.
Yeah.
Hi, Max. Hi. Yeah. So your host actually, yeah, sort of touched upon a bit on the whole thing with pot to pot, and in a former job, I had a sort of issue where we had one camera manufacturer. We'd used them for about 5 years, and then we're going to switch to a different camera manufacturer, and we're like, well, our model's going to perform the same way with the new cameras, and we've gathered 2 years of data on one camera. Do we have to wait until we have 2 years of data to keep our performance? And it's like, I don't know, have you ever dealt with that situation, and how, I don't know if you have any, I know you're more on the hardware side. It's like, what do you do?
So the answer is, there's a couple of different ways to answer that. The first is, it depends on how much of a change you're making to your hardware. So if it's the identical camera module,
no,
so
it's
completely new,
yeah,
completely new.
Yeah, it's like one was made in Germany, the other was made in China.
And
it was different, sort of like different use. One was machine vision, one was like a security camera.
so you can definitely train on your existing data, but it will never be as good as if you had a completely new data set. But I would definitely augment your existing data set with images from your new camera, so that way it's a little bit more robust to that change in image quality. So as an optics person, I'm always concerned about the change in distortion. And so one of the examples earlier is that if there is a very substantial change in distortion, it can throw off your network. So my answer is don't throw out your old data set because it's still 100% valid, but you may need to make it more robust to your new hardware system. And on the hardware side, I would definitely recommend trying to get your new manufacturer to be as close to your existing hardware as possible.
Is there a way of like calibrating, the second question, is there a way of calibrating one, like let's say you had 1,000 images from the old camera, is there a way of calibrating the new camera almost to say, I want the new camera by processing the software to look like the old images? Does that make sense also?
Yeah, so I would actually approach it from a slightly different standpoint, which is how to use your existing photos for your new system. So I would, there are ways from the synthetic data world, which are fairly physically realistic. So you could construct some sort of mapping function between color and distortion from your old camera model to your new one. And that way, if you run your entire your old data set of images through that mapping function, it will be closer to your new model than just training on that old data. So I would say it depends on what the difference is, because some of those mapping functions are much more complicated. But if it's just a matter of lens MTF, there are some research papers showing how you can do physically realistic blurring. And so, I would say definitely keep your old data because it's very valuable and it's, you've worked so hard to capture it. So,
awesome. Thanks.
Yeah.
Thank you. Great question. Following on from the earlier question, when it comes to ghosting, how important do you think it might be to actually train for ghosting? Because I know as a human being, I recognize ghosting, well, maybe because I'm in optics, but being able to recognize ghosting and say that's ghosting, it's not a face, or whatever other object it might be. And I haven't seen any attempts to do that. Have you seen anyone actually training on ghosting so they know then to not categorize it as something else?
That's an interesting question. As an optics person, I always say, well, let's get rid of the ghosting. It's difficult. But from a software standpoint, I think if you look at, ANSYS, they have a group which they do some physically realistic synthetic flare that you can actually train on.
SPIOS tool?
I think so.
Yeah, it's a SPIOS,
Additionally, more data is better data when it comes to real-world performance. So if you do capture images from your camera system, those will make their way into your neural networks, and it will become more robust over time with those ghost artifacts throughout the data set. I haven't seen anything, as intricate as like the geometric synthetic data, which allows you to reorient objects in the input for training data. So I haven't seen anything like that for ghosting, but maybe soon.
Next question, please.
Hey, thank you for your comprehensive presentation. Hey, so I have a question with regard to noise. So first of all, I have been developing, variety of image sensor for, the many applications, and usually, when it comes to photographic camera sensor, everybody look for low read noise floor. But when I work with, maybe this is just my experience, but when I talk with machine perception or CV people, they are more interested in the potential limited region instead of the extremely low noise performance. So my impression was maybe CV engineers or machine perception engineers has a kind of low limit in terms of SNR. So as long as they have they get a sufficient SNR in photon shot dominated regime, then they are fine. So they don't care about the noise floor. So is it true statement, or I would like to learn about this?
So I don't have a direct answer for that because that is I would maybe refer you to the paper. At that point, because I don't want to say something that's inaccurate. So that's a good
your
point.
Personal opinion.
Yeah, so if I just take a guess, The photon shot noise is probably more problematic because it's more visible. But you can augment your data set using artificial noise, and so that might make the network more robust to specific types.
So when it comes to low light situation,
Yeah.
is there any criteria CV engineers consider as a valid signal, and below that criteria you just consider them garbage data? Is there any such a criteria?
That would depend on the network that the computer vision engineer is deploying. So the answer to that is situational.
Okay. Case by case.
Yeah, case by case, because if you're doing line detection, that's completely different than doing some of the newer topologies in classification.
Okay, understood. So
Yeah.
I will try to experience more.
Yeah, well, no, I would say it's, there's definitely research out there on this topic, and it's just a matter of going down that rabbit hole and finding all the research papers related to it.
All right, thank you.
Yeah.
It is a very good point. A lot of the time, with read noise being so low in modern image sensors, that often you are in the photon shot noise limited regime. If you have 100 photons, you've got 10 read noise of, a photon shot noise of 10. Or if your read noise is only 2 electrons, then it's clear what's dominating in that case. And yeah, you've really got to do the analysis on the individual system, your illumination, your F number, and integration time. It's a very relevant topic. Any final questions? And once again, thank you to Max.